Yesterday we had started with a chapter called as chemical kinetics. So we are going to build the foundation of the chapter today and then go on to solve higher level problems. Okay, so just let's start with the lecture now. So in the previous lecture we have talked about rate of a reaction, right? We have defined the rate of a reaction as change in concentration per unit time, right? And we defined two types of rate, that is instantaneous rate and an average rate. Then we went on to solve some questions. We also defined the overall rate in the last lecture. So now let us see if the reaction which has been given to it, all of the reactants are in gases, okay, or the product formed are also in the gases. So basically when we are having the entire reaction in gaseous medium, we can also express the rate in terms of the change in their partial pressure. Just like the way we are doing as change in the concentration, now we can express the rate as change in their partial pressure, because when gases will react, their amount or their moles will change. Now when their moles changes, when it decreases, so the partial pressure would also decrease. So basically we will monitor the rate by like calculating the change in the pressure. So just take an example to understand this. So we are saying that rate can also be expressed as change in pressure or change in partial pressure upon time taken for that particular change, okay. So basically suppose we are having a, say a reaction something like this, gas A is changing into say a B gas, okay. So we'll define rate as rate of disappearance of A would be defined as the change in partial pressure of A, that is final pressure minus initial pressure. Because it is a reactant, so we have to include a negative sign. So this will be the change in pressure of A, final pressure A of pressure of A finally minus pressure of A initially upon time taken, okay. So we can write this as minus delta PA upon delta T, right. It is similar to what we were doing when we are doing in terms of concentration. So if we want to suppose calculate rate of appearance of B, so we know that initially B was not formed, so the partial pressure of B at the start would have been 0. So we will define this as the final pressure of the final partial pressure of B minus initial partial pressure of B divided by time taken, okay. So this will have a positive sign only because this is product. So basically this will be delta PB upon delta T, okay. So I hope this is clear to everyone. So this is just in accordance with the same formula which we had done yesterday, okay. So just remember this point. We can also express the rate in terms of change in pressure per unit time. So basically the unit of rate then would become, suppose the unit of pressure is atm and time is measured in second, so the unit of rate would become atm per second. Now if we were using the rate as change in concentration per unit time, then its unit was moles per liter per second or molar per second, okay. So just write it quickly. Okay. So let us derive a relationship between the two kinds of rate. So we know that generally the gases are ideal, or at this level we assume that they are behaving ideally. So basically we know that ideal gas equation says that PV is equals to nRT. Now from that we can calculate N by V. So basically this N by V is also the concentration, right, number of moles per unit volume. So this will be equal to P upon RT, okay. So we are defining the rate as change in concentration. Suppose we are writing in terms of reactant. So this was basically minus del C upon del T. So what we'll do, we'll just put the value of C as P upon RT. P will be the partial pressure of that particular component whose rate we want to calculate. So they basically, because R and T are constant, the reactions are carried out at a particular temperature. So temperature is constant, R is a gas constant. So we can take it out. So this will basically become minus del P upon del T. Okay. So this is the relationship between rate in terms of concentration, defined in terms of concentration, and defined in terms of partial pressure. So if we are writing it for the product, same expression would come. So basically it is delta C upon delta T, right? This represents that we are writing it for product because the concentration is increasing. So this will be delta partial pressure of that component upon RT upon delta T. We know that R and T are constant in the reaction, only partial pressure is changing. So we can write this as delta P upon delta T into 1 by RT. Okay. So this is the expression. So this is the relationship between rate which is expressed in terms of concentration and the rate which is expressed in terms of partial pressure. So just note it down. Okay, so I hope everyone is noting it down and is having a copy and a pen with him while viewing the lectures. Okay. So just let's solve this question first. Okay. So take out your copy, start solving this. So this basically says that for the reaction at 273 Kelvin, where we are reacting NO gas with ozone and forming NO2 gas and O2, it is observed that the partial pressure of NO gas falls from 700 millimeter Hg to 500 millimeter Hg in 250 seconds. Calculate the average rate of reaction in atm per second and in the second part molar per second. So basically these questions are very easy, just I am making sure that you are able to do the unit conversion properly. Okay, so this is the main highlight in physical chemistry, because we have to carry out a lot of calculation and unit conversion, and these are the very small mistakes that a student often make. So please ensure that whatever is the unit, like whatever the question is asking, you have to bring the particular calculation in that particular unit. Okay, so just try this now. So basically in this question again everything is given in terms of pressure. So we will say that average rate will be equal to, because we have been given the pressure of NO gas, so basically we have been given the reactant. So the average rate would be minus final pressure of NO. So NO comma F means final pressure of NO minus initial pressure of NO divided by time taken. Okay, so basically this will be T2 minus T1. Okay, so the final pressure given to us is 500 and the initial pressure given to us is 700 and the time taking is 250. Okay, so basically when you calculate, this comes out to be 200 upon 250. But remember that the pressure is given in mm of Hg. So we need to convert that pressure into the atmosphere. We know that 760 mm of Hg corresponds to 1 atm. Okay, so 1 mm corresponds to 1 by 760 atm. So basically if you divide by 760 you will get the pressure in atm, right. So this becomes the answer in atm per second. Okay, so basically this is 500 by 760 atm minus 700 by 760 atm. 760 we have taken common, so this is basically 200 upon 760. So we will calculate in terms of atm per second. Okay, so you can calculate this now. So you can just this is 4445. So basically this is 1 by 4 ones are 4 3 190 into 5. Okay, I think this is the calculation over here, because this is 5 4s are 5 5s are, and this is 190. Okay, so basically this is the answer in atm per second. Okay, now we want to calculate the same in moles per liter per second, that is we need to change it in concentration term. So we already know that delta C by delta T was equal to 1 by RT into delta P by delta T. Okay, so we know the value of delta P by delta T. So you can put R as 0.0821, right, because pressure is in atmosphere. So R will be 0.0821 liter atmosphere, okay, per mole per Kelvin. Temperature you have to take in Kelvin. Okay, so temperature is not given over, temperature is given as 273. So this is the value of RT into 1 upon 5 into 190. So when you do the calculation, you will get this in molar per second. Okay, so this is a very easy question, but it makes you do a lot of calculation. And remember, in JEE, calculation is a very important technique. If you are weak in your calculation, then probably getting the answer, especially in the integer type question, will become difficult, because the margin of error in that particular question is very less. So if you are weak in relatively number crunching, or you are not able to do the calculation fast, ensure that you are solving more of subjective questions, and while solving you are trying to calculate everything. Okay, so just ensure that you are doing your calculations. Okay, so okay, this you can do it. Now let us start the very important topic, that is rate expression and rate constants. Okay, so basically everyone might have an idea of chemical equilibrium. Okay, so there we studied one law which is called as law of mass action. Law of mass action was basically given by two scientists who were Goldberg and Wage. Okay, so basically law of mass action says that the rate of any chemical reaction is directly proportional to the active mass of the reactant raised to the power some factor. Okay, that factor may or might not be equal to the stoichiometry. So this was the law which was given by Goldberg and Wage and is called as law of mass action. So basically this law says that the rate of a chemical reaction is proportional to the product of active mass of reactant raised to the power some factor. So you can write this down, raised to the power of some factor. Okay, so basically suppose we have been given, say, a chemical reaction something like this, A plus say 2B changing into C plus D. Okay, so we'll say that the rate of this chemical reaction will always be proportional to the active mass of, okay, active mass of reactant. So in this case one reactant is A raised to the power some factor, suppose this factor is X, into the active mass of the other reactant raised to the power some factor Y. Okay, so now we need to understand what is this active mass exactly. Now active mass is basically that mass of the substance or the amount of the substance that is reacting in a chemical reaction. Okay, suppose you are mixing A and B, some amount of A would be reacting with some amount of B. So basically active mass is the amount of the substance or the amount of that species which is reacting in a particular chemical reaction. Okay, now generally we say that activity is generally equal to activity coefficient into concentration, right? So this is just something like which we have done in ion equilibrium as well, that is pH was minus log of activity of H plus, okay. So basically here we define activity as a coefficient, activity coefficient into concentration. Now generally, because while dealing at this level and generally we carry the reactions in the lab which are generally dilute in nature. So for dilute solution generally the value of activity coefficient is 1. So we directly say that the activity and the concentration are the same thing. So at this point of time, at this level of understanding, we will assume that the activity and the concentration are same, because the activity coefficient is 1 for a dilute solution. So basically we will say that the rate of a reaction is proportional to the concentration of A, right. Square bracket means that we are expressing in terms of concentration raised to the power x into concentration of B raised to the power y, okay. So this is the basic rate law equation, okay. So basically law of mass action says that the rate of a chemical reaction is proportional to the product of active mass of the reactant raised to the power some factor, okay. And we know that the active mass is an activity coefficient into concentration term, okay. Now we say that for dilute solution this activity coefficient is 1, so we assume the active mass to be equal to concentration, okay. So when you remove this proportional sign, we will get a constant K, okay. Now this K is called as rate constant, okay. So basically if any reaction is given to you, can we write directly by looking at the chemical reaction its rate equation? We can never write the rate equation just by looking at the chemical reaction. We need to have some experimental values, experimental data to understand the rate equation, okay. So basically we will say that rate of a reaction is proportional to the concentration of the reactant raised to the power some factor, okay. Now that factor may or may not be equal to the stoichiometry. How we will come to know whether it is equal or not? We have to find it experimentally. Any theoretical knowledge won't help us there, okay. So if suppose we are having more than one reactant, then we will say that the rate of a reaction is proportional to the concentration, the product of concentration of the reactant raised to the power some factor, okay. So basically this becomes the rate equation, and the value of K is, which is called as rate constant, is a fixed value for a particular reaction. So basically rate constant is fixed for a particular reaction. So just write it down. I hope this is clear to everyone. Okay, so how we define rate constant? Okay, so basically we say that rate constant or K is equal to the rate of the reaction when we take the concentration of the reactant as 1 molar. Suppose they are 1 molar, so obviously 1 raised to power x and 1 raised to power y is 1. So the rate constant will become equal to the rate. So basically the rate constant is defined as the rate of a reaction with unit molar or with unit concentration of reactants. Okay, so this is how we define the constant. Now we know that this is a fixed value for a particular reaction. Whenever a particular reaction is occurring, it will have a fixed value. So this K is a constant, it just depends on the temperature, right? If you change the temperature, the value of K will also change. This we are going to discuss in detail when we come to the later part of the chapter, that is dealing with Arrhenius equation, okay. So basically at this point of time we will define that rate constant is basically the rate of a reaction of a unit molar concentration of reactant. So basically the rate constant measures the rate of a reaction. more is the value of K, more is the value of rate constant, more or the faster would the reaction be. Smaller is the value of rate constant, it means that the reaction is very slow. Okay. I hope this expression is clear to everyone now. So just look at some important parameter over here. So basically we are saying that suppose we are having any reaction, say 2A plus 3B. Okay. Now this is giving a product, say C plus 4D. So suppose we have to write the rate equation, what will say that rate is equal to the rate constant into concentration of A raised by some factor, say it is P, into concentration of B raised by some factor Q. Okay. I hope this expression is now clear to everyone. Now this P can be equal to 2 and this Q can be equal to 3, which is their stoichiometric coefficient, but we cannot comment it directly, we have to verify it experimentally. Okay. So basically if you look at P or Q, now they are called as order of reaction, okay, with respect to P is order of reaction with respect to, suppose I am writing just P. So basically it is order of reaction with respect to P, and Q is called as order of reaction with respect to Q. Okay. So basically if we want to find the overall order, we will say that overall order is P plus Q. Okay. Now how we will get the value of overall order? I will explain you little later. Okay. So basically these terms are called as order. P is order with respect to A, Q is order with respect to B. Overall order of this reaction is the sum of the factors. Okay, that is P plus Q. Okay, just write it down. Okay, so I hope this is clear to everyone. Now let us understand the characteristics of rate constant. Now whenever we are writing a rate equation, there will always be a rate constant which is K. So basically it is the measure of the rate of the reaction. I have already told you, more is the value of rate constant, higher is the value of the rate constant, faster would be the reaction. Smaller is the value of rate constant, like the speed of the reaction or the rate of the reaction would be slow. Okay. So basically rate constant measures the rate of reaction. Now we also say that different reactions have different rate, because obviously we know this from our, like, only we can observe in nature also, all reactions does not proceed at an equal rate. Okay. Some proceeds in a faster manner, some proceeds very slowly. Common example is rusting. Rusting of iron takes like a very long time to happen, whereas suppose burning is done very quickly. So basically the burning reaction will have higher rate constant value and the rusting of iron would have smaller value of rate constant. So we say that rate constant is a characteristic of a reaction, okay, and it determines the rate of the reaction, and it has a different value for different reactions. Okay. So the value of K is constant at a particular temperature. Okay, this I have already told you that the K is a constant at a particular temperature, but it will change if you change the temperature. Okay. Okay. Sorry, the rate constant is independent of, this is not temperature, this will be concentration. So the rate constant is independent of the concentration. Okay. So basically these are the characteristics of rate constant. We will study the unit of rate constant when we have defined order of reaction very properly and we have studied some cases. Okay. So just have a quick look, or you can have a snapshot, or you can write this in your copy. Okay. So theoretical questions comes on the characteristics of rate constant also. So rate constant is a fixed quantity, fixed value at a particular temperature, will change only with change in temperature. It is independent of the concentration of the reactants. Okay, all reactions will have a specific rate constant value. So reactions have different rate constant, and basically rate constant of a reaction tells us about the rate of the reaction. Okay, so we can predict knowing the value of rate constant which is faster or which is a slower reaction. Okay. So now just let us study the main concept that we wanted to cover today, that is order of reaction. Okay. So I have already told you, before understanding order of reaction, okay, let me explain you two types of reaction. One is called as an elementary reaction. Okay. So basically an elementary reaction is a reaction which occurs only in one step. Okay. So elementary reaction is a reaction which occurs in a single step. Okay. Common example, if you have covered in organic chemistry, common example is a SN2 mechanism. It is a single step mechanism, right, where say we are having an alkyl halide. So if someone has not covered, don't worry about it, we'll cover it when we do organic. So basically you take an alkyl halide, to this you add any, say KOH, to this you add any nucleophile. Okay. So this OH negative attacks at the carbon, X goes out and we form alcohol and KX. Okay. So this is basically an example of SN2 mechanism. So SN2 mechanism occurs in a single step. So those reaction which occurs in a single step is called as an elementary reaction. We would need the knowledge of elementary reaction to understand order of reaction. Okay. The second is a complex reaction. Okay. So complex reaction is basically a reaction which is having more than, or which proceeds in more than one step. Okay. So which occurs in more than one step. Okay. So we say that they have more than one elementary steps. So they have more than elementary steps. Okay. So basically a complex reaction is one which has more than one step. Suppose a very common example is a SN2 reaction, SN1 reaction. So what happens in SN1 reaction, like we take an alkyl halide, it breaks into a carbocation and X negative. Okay. And in the next step, in the second step, a nucleophile attacks on it and it forms a species something like this, and in the last step this will lose a H positive and form alcohol. So basically I will say that if I add all these steps I will get the overall reaction. So the overall reaction would be Rx plus water forming ROH plus say HX over here. Okay. So basically this reaction Rx plus H2O forming ROH plus HX is not a single step reaction, is not an elementary reaction. This is made up of three steps. So basically these are the three steps. Now each step will be a elementary reaction because they are occurring in a single step. Okay. So these are individual elementary reaction. So this complex reaction contains three elementary reactions or three steps. So all those reactions which are occurring in just one step is called as an elementary reaction, and complex reactions are those which have more than one step or more than one elementary step. Okay. So just write it down quickly. So the common example of this is SN2, the common example of this is SN1 reaction. Okay. If you have not encountered these words, no need to worry because these are anyways independent topics. So just write it down. Okay, you can take any example, say something like this: AB reacts with C and forms AC plus B. So this is happening in one step. This is just a hypothetical reaction occurring in one step, so it is called as an elementary reaction. Similarly, you can write any reaction which can happen in more than one step. Okay. So I hope this concept is clear to everyone. Now let us understand the concept of order. Now we have already said that suppose we are having a reaction, say A plus 2B forming C plus 3D. Okay. Now suppose if we want to write the rate equation of this reaction, we will say that rate is proportional to the concentration of A raised to power some factor into concentration of B raised to power some factor. Okay, and when you remove that proportional sign, a rate constant will come out. So basically this is the rate expression. Okay. Now the power to which the reactant has been raised, or the power to which this reactant has been raised, will be called as order of reaction with respect to A. The factor with which the other reactant has been raised will be called as the order of the reaction with respect to B. So basically this A and B is called as the order of the reaction, and if we take the sum of it, then we will call as the overall order. So basically overall order of this reaction would be A plus B. Okay. So we will see what it signifies. So basically the sum of the powers to which the reactant has been raised in the rate law expression is called as order of the reaction. Okay. So just write it down. Now how we will come to know about this A and B? Okay. Suppose we have taken a reaction. Okay. Suppose we have started a reaction A changing into B. We don't know what is the order with respect to A. Okay. So what we do is we start with say a 10 molar concentration and we measure the rate. Okay. Then what we do? We change the concentration of the reactant. We change it to say 20 molar, and then we will record the rate. Okay. We will record the rate of the reaction. So on changing the concentration, the rate of the reaction would also change. Okay. The factor by which the rate of the reaction is changing by changing the concentration of the reactant is generally order of this reaction. Okay. So basically when you are having a reaction, say something like this, A plus 2A plus 3B changing into C plus say 4D. So basically rate is K into concentration of A raised to power A into concentration of B raised to power B. So now we know that order with respect to A is A, order with respect to B is B. Okay, and the overall order is A plus B. Okay. So basically we are saying that order is an experimentally determined quantity. So this is basically an experimentally determined quantity. We cannot comment about the order of the reaction just by looking at the equation, because its stoichiometry is 2, we cannot say that the value of A will be 2. The stoichiometry of B is 3, we cannot say that the value of B will be 3. We have to check it experimentally. So we say it is a experimentally determined quantity. Now how it is checked experimentally, what we will do? We will vary the concentration of the reactants. Okay. So we will vary the concentration of the reactants, and every time we will measure the rate of the reaction. Okay. And by taking the ratios, we will able to find out the order of the reaction. Okay. So basically order of the reaction tells us about the effect of change of concentration on the rate of a reaction. Okay. Now a very important point which you should understand, that for elementary reactions, so whenever we are having a elementary reaction, we will say that the order will be equal to stoichiometry. Okay, because the reaction is happening just in one step, so obviously the rate of reaction will be dependent upon the reactant, concentration of the reactant. Okay. So in that case we will say that order is equal to stoichiometry. Okay. Suppose we say that A changing into B, this is a elementary reaction, so we will say that rate will be equal to K into concentration of A raised to power 1, because the stoichiometry is 1. So in that case we will say that order and stoichiometry are same. Similarly we say that 2A is changing into say B. So in this reaction, suppose it has been told to you that this reaction is also elementary, So we'll say that rate is equals to K into concentration of A raised power 2. Okay. Now suppose this reaction was, hypothetically we are assuming, suppose this was also said that this is an elementary reaction. So the rate of this reaction would become K into A raised power 2 into B raised power 3. So order with respect to A would have been 2 and order with respect to B would have been 3. Okay. Just write it down. So for elementary reactions, we say that order is equal to stoichiometry. Okay. So now what about complex reactions? Okay, or the reactions which is having more than one step. Okay. Now suppose we are taking a reaction, say A2 plus 2B changing into say AB. Okay. Now suppose it has been said that this reaction is a complex reaction and its mechanism is something like this. So first A2 is reacting B and forming A2B, okay, and then this A2B is combining with B and forming AB. Okay. Suppose we have been, this is just a hypothetical assumption, suppose a reaction has been given to you and this has been said that this reaction follows this mechanism. Okay. So the first A2 reacts with B and forms A2B, and then this A2B reacts with B and forms AB. Okay. So this is the mechanism that has been given for this reaction. Now this reaction is made up of two reactions. So basically this reaction is made up of two elementary reactions. Now we obviously know that both of the reactions would have different rate constants, because reactions would have different rate constant. So suppose the rate constant of this reaction is K1 and rate constant of this reaction is K2. Okay. Now between the two, okay, whichever step is slower, that will determine the rate. So basically let us assume that the first step is the slowest step. Okay. So basically in case of complex reaction, we say that the slowest step determines the rate. Okay. So slowest step will be the rate determining step. Okay. So we'll call this as RDS, rate determining step. Okay. So just take an example. Suppose like there is this big company who is producing cars. So basically the production of car, that is when a car is produced and brought in the market for sale, obviously there are many parts that has to be incorporated in that car. Okay. So there are different division in the industry. One who is preparing the body of the car, the other who is preparing the seat and the seats, the other department who is taking care of the electronics, and the other department which is taking care of tire, and say other department which is taking care of the engines and all the other equipments. So basically there are 5 departments. So basically a production of car is done through these 5 processes. Okay. Now among these 5 processes, the one which is taking like most of the time, okay, suppose the construction of engine, the fitting of the engine or the equipments that are attached to it is taking most of the time. So the rate of production of car is basically dependent on the rate at which the engines and the other equipments are getting installed. So basically we'll say that the rate of production of car is dependent on the rate at which the engine equipments are fixed in the car. So basically the one which takes most of the time in the reaction is often said to be determining the rate of the reaction, because in that particular, if you consider these two reactions, this is the time when the reaction has spent most of the time. Okay. So this is the step in which the reaction has spent most of the time. So if we study this first reaction, we will be able to tell more about the reaction mechanism. So basically whenever we are having a complex reaction, so there would be obviously say 2, 3 or 4 or any number of steps. The one which is having these, like the one which is the slowest among them will determine the rate of the reaction. Okay. So in this case the first step is RDS. Okay. So basically the rate of this equation would become, now because this is an elementary reaction, individually 1 and 2 are elementary reaction because they are happening in one step. So because this is an elementary reaction and the rate of this reaction is dependent on this step, so we'll directly say that rate is equals to A2 raised to power 1 because its stoichiometry is 1 into concentration of B raised to power 1. So we'll say that order of this reaction with respect to A is 1 and with respect to B it is also 1. So total overall order we can say that it is equal to 2. Okay. So I hope you got my point. Okay. Now let us look at this point in some different way. Now suppose this reaction has been given to us A2 plus 2B saying giving 2AB. Now somehow suppose we know that the overall order is 2. Okay. So if we look at the equation, the stoichiometry of A2 is 1, stoichiometry of B is 2. So if this would have been an elementary reaction, the order of this reaction would have been 3, right? But because order is given 2, it means that this is not a elementary reaction, it is a complex reaction made up of more elementary steps. So we have to see their elementary steps, and the elementary step which is slowest will determine the rate of that particular reaction. So we'll just take out the RDS, RDS is the second step, okay, RDS is the first step in this case, and the order with respect, because it is elementary reaction, so order and stoichiometry will be same. So order with respect to A2 is 1, order with respect to B is 1. Okay. So this is how you understand whether a reaction is elementary or not. If reaction has given to you and the stoichiometry and order are matching, it means that it is a elementary reaction. If they are not matching, that means it is a complex reaction made up of more elementary reaction, and one of these step is the rate determining step, okay, which is determining the rate of that particular reaction. Okay. So just have a quick look, you can have a snapshot, you can write it down. So basically we cannot comment on the order of the reaction just by looking at the stoichiometry. So what we have to do, we have to calculate it experimentally. And how do we calculate it experimentally? We calculate it by changing the concentration of reactant and measuring the rate of the reactions. Okay. So when we keep on changing the concentration, the rate of reaction will keep on changing. So the factor with which the rate of the reaction is changing is the order of the reaction. So that is how we do it in laboratory, which is an experimental way to find out the order of a reaction. Okay. So I hope this is clear to everyone. So now let us understand the units of rate constant. Okay. So let us define first. Now one which important thing which I forgot to say is order of a reaction can be negative, fractional or integral. Okay. So order can take any value. Okay. Suppose you are changing the concentration of a reactant and rate increases say 1.3 times. So basically the order would become 1.3. Okay. So basically it can be fractional, it can be negative, or it can be integral, or it can also take a value of 0. Okay. So basically this is a very important point, right. So let us consider few example. Now suppose we are talking about a 0 order reaction. Okay. So 0 order reaction, we will say that its rate equation would be something like this: rate is equals to K into concentration of reactant raised to power 0. Suppose we are considering a hypothetical reaction A changing into B. So suppose it is said that the rate of this, the order of this reaction is 0, it means that rate is equals to rate constant into concentration of A raised to power 0. So the order of this reaction would be 0. For say first order reaction, okay, so if order is 1, we will say that the reaction is first order. Okay. So for this reaction, suppose this reaction is first order, so we will say that the rate equation will be K into concentration of A raised to power 1. If it is a second order reaction means the order is 2. So we will say that rate is equals to K into concentration of A raised to power 2. If it is a third order reaction, we will say that rate is K into concentration of A raised power 3. Okay, so I hope this is very clear. So if we look at the units of rate constant, okay, so we know that the unit of rate is generally change in concentration per unit time. So it is moles per liter per second or molarity per second, because the order of this reaction is 0. So basically the unit of rate constant will be equal to that of rate constant. So unit of K in this case would be moles per liter per second or molar per second. Okay. So sometimes in a question you have not been given the order of the reaction directly. Somehow if you read the question in the data of the rate constant, the unit would have been written as mole per liter per second, indicating that it is a 0 order reaction. Okay. Now for first order reaction, we know that the unit of rate is moles per liter per second and the unit of concentration is moles per liter. So this basically gets cancelled out. So the unit of rate in this case is per second. Okay, so these are the unit. So for a first order reaction, the unit of rate constant would be per second. Now let us consider a second order reaction. Okay, so we know that rate unit is moles per liter per second, and because we are squaring this, so basically it will be mole square liter square. Okay, so if we cancel out this, so we'll get the unit as mole inverse liter per second. Okay, so this is the unit for a second order reaction of rate constant. If you consider third order reaction, so basically the unit of rate is mole per liter per second and the concentrations are raised by 3. So basically they will become mole inverse square liter square per second. So this is the unit of rate constant for a 0 order reaction, that is molarity per second. First order reaction it is per second. For a second order reaction it is per mole liter per second. Okay, and similarly you can calculate for the third order reaction. Okay, so this is a very basic that you should know, because directly looking at the value of the rate constant we will be able to predict the order of the reaction. Okay, so if we are defining say any general reaction say of the order n, so basically rate is equals to K into concentration of A raised power n. So we will say that the order of this reaction is n. So the unit of K in this case would be, we know that the rate unit is mole per liter per second and the unit of concentration is mole per liter. So this is raised to power n. So when you put over there, so this becomes mole 1 minus n liter n minus 1 per second. So this is the general unit of rate constant. We can also verify it. If it is a 0 order reaction, the value of n would be 0. So this will come out to be mole per liter per second. If it is a first order reaction, n is equals to 1. So when we put it 1, so this will be per second. So if the order is 2, then the value of n is 2. You put the value of n as 2. So this is per mole liter second per second. And similarly you can check for third order reaction or any fractional order reaction as well. Okay, so just write it down now. So basically we say that order is basically an experimental finding, okay, and the order can be either 0, it can be fractional, it can be integral. Okay, so basically order is the order signifies the change in the rate or the power by which the rate changes when the concentration of reactant are varied. Okay, I hope this is clear to everyone. Now before going to the molecularity, just take this question to understand the concept of order. So basically this says that for the reaction A plus B changing into C plus D, doubling the concentration of both the reactant increases the rate by 8 times, and doubling the initial concentration of only B simply doubles the reaction rate. What is the rate law for the reaction? Okay, so this is how experimentally we calculate rate. Okay, So let us assume that rate of this reaction is K into concentration of A raised power A into concentration of B raised power B, where A is the rate with respect to A and B is the rate with respect to B. So it is saying that on doubling the concentration of both the reactants. Okay. So suppose this was our initial rate, we are writing this R0. Now when we are doubling the concentration of A and doubling the concentration of B, okay, this saying that the rate increases by 8 times. So basically this becomes equal to 8 R naught. Okay, so this will basically become K into 2 raised power A into A raised power A, 2 raised power B into B raised power B. So this is basically 8 R naught. So basically I can write this as 8 into K into A raised power A into B raised power B. Okay, so the rate is increasing 8 times, that means it becomes 8 R naught, that is increases 8 times. Okay, so if you cancel this out, right, so we get this as 2 raised to power A plus B equals to 8 can be done as 2 cube. So basically we get A plus B as 3. Okay. Now the second part of the question says that and doubling the initial concentration of only B. Okay. So basically now we are doubling the concentration of only B. Okay. So we write this. So we doubled the concentration of B, so it became 2B. Now the rate simply doubles. Okay. So basically the rate doubles of that of initial rate. So we can say that K into A raised to power A into 2 raised to power B into B raised to power B is equals to 2 times K into A raised to power A or concentration of B raised to power B. So all these terms get cancelled out. So we get 2B, 2 raised to power B equals to 2 raised to power 1. So basically the value of B comes out to be 1. Now we know that A plus B is 3, so A will come out to be 2. Okay. So the rate of this reaction would be K into concentration of A raised to power 2 into concentration of B raised to power 1. Okay. So this is how you calculate it experimentally. Okay. I hope this is clear to everyone. Okay. Just have a look at this question now. This question says that the reaction A plus B plus C changing into D plus E is found to be first order in A. Okay. So this is basically first order with respect to A. So this is concentration of A raised to power 1. I am writing the rate expression, and second order with respect to B. Okay. And 0 order with respect to C. Okay. So this is the rate equation that has been given to us. Write the rate expression. So this is the rate expression. Okay. Now this question says that what is the effect on rate on increasing the concentration of A, B and C 2 times. Okay. So if we are increasing the rate of A 2 times, okay, and rate concentration of B 2 times and concentration of C 2 times. So basically I am writing 2A, means we are doubling the concentration. So this will become, we will take out 2. So this is 2 into 2 square. So this is 8 into K into A raised to power 1 into B raised to power 2 into C raised to power 0. Okay. So basically rate is equal to 8 times that of initial rate. So the rate would increase 8 times. Okay. I hope this is clear to everyone. Okay. So this is what I meant to say when we started order. Suppose we are having, okay. Now suppose how do we calculate the rate, the order of this reaction? Okay. Suppose we took some concentration and we carried out the reaction. Now we doubled the concentration. On doubling the concentration, it was observed that rate also doubled. It means that order with respect to A would have been 1. If suppose we increase the rate to say 3 times, and suppose the order, the new rate came to be 9 times of the original rate. So basically the order would have been 2. So this is how we calculate in lab. Okay, just we keep on varying the concentration and we keep on measuring the new rates, and we can say what the order of that particular reaction is. Okay. Now just do it so that I will get to know whether you are understanding or not. So basically this says that for a reaction 3A changing into product, the rate of reaction doubles if the concentration of A is increased 4 times. Calculate the order of reaction. So let us assume that rate is K into concentration of A raised power n. Okay. So what it is saying, that it is found that the rate of reaction doubles. So basically the rate of the reaction doubles, okay, if the concentration of A is increased 4 times. Okay. So we are making the concentration 4 times. Okay. So we know that rate is K into A raised power n. So this is basically 4 raised power n into K into A raised power n. So this term gets cancelled out. So basically 2 is equals to, we can write this as 2 square. So this is equal to 2n. So basically 2n is equals to 1 and n will get as half. Okay. So I hope this is clear to everyone. So these are the very basic question that you need to address. Okay. Okay, we will talk about molecularity little later, because molecularity is like currently not that much important, but we will talk about molecularity. First we need to understand the concept of order. Okay. So let us skip this question for a while. Now let us see a reversible reaction. Now we know that a reversible reaction is the one which will happen in both the direction, that is forward as well as backward. So let us consider an equilibrium reaction something like this. A plus B is changing into C plus D, okay, and let us assume that it is a elementary reaction. Okay. K1 is the rate constant for the forward reaction and K2 is the rate constant for the backward reaction. Okay. So if we write the rate of this equation, okay, so the overall rate of this equation would be, we will say that overall rate is rate of forward reaction minus rate of backward reaction. Okay, so the rate of this reaction would be rate of forward reaction minus rate of backward reaction. Now the forward reaction, A and B will be acting as reactant. Okay, so the rate of forward reaction would be K1, because it is an elementary reaction. So order with respect to A is 1, order with respect to B is also 1. So rate will be rate constant into concentration of A raised power 1 into concentration of B raised power 1 minus rate of backward reaction. Now when we consider backward reaction, the reactant for backward reaction is C and D, okay, elementary reaction. So the order would be 1 with respect to C as well as D. So basically rate of forward reaction would be rate constant K2 into reactant concentration raised power the stoichiometry. So basically C raised power 1 into D raised power 1. Okay. So this will be the overall rate for a reversible reaction. Now we know that at equilibrium, when equilibrium is attained, right, overall rate becomes 0. So overall rate becomes 0. That means both forward and backward reaction are proceeding with a equal extent and with a equal speed. So basically the rate of the reaction becomes 0. So when you put this value as 0, so we get that K1 into A raised power 1 into B raised power 1 is equals to K2 into concentration of C raised power 1 into D raised power 1. So we can write this also as K1 by K2. This will be equal to concentration of C raised power 1 into concentration of D raised power 1 upon concentration of A raised power 1 into concentration of B raised power 1. This is also your equilibrium constant Kc. Okay, so basically equilibrium constant is the ratio of rate constant of forward reaction divided by rate constant of backward reaction. Now this we have done in chemical equilibrium, but let us revisit it. Okay, so basically we have written the overall rate, which is for a reversible reaction, which is rate of forward reaction minus rate of backward reaction, and then we equated it with 0 because in equilibrium rate of forward and backward reaction becomes equal. Okay. So basically we got the value of equilibrium constant as rate constant of forward reaction upon rate constant of backward reaction. So we can write that equilibrium constant is always rate constant of forward reaction divided by rate constant of backward reaction. Okay, I hope this is clear to everyone. Okay, you can write it down as well. So till now we have done a very important concept of order of reaction. Okay, we have also defined how do we write rate expression. Okay, so we have written a rate expression and we have defined order of reaction with respect to the reactant as well as the overall order. Okay, and we have done the significance of rate constant, unit of rate constant. We have still not talked about molecularity, which we are going to discuss, but let us first deal with order so that it becomes more easy to understand. Okay, so I hope everyone has written this now. Now let us first discuss a zero order reaction. Okay, what exactly is zero order reaction and how we'll write its rate differential equation as well as integrated equation. Okay, so let us assume that there is this reaction A changing into B. Okay, suppose this reaction is proceeding with a rate constant of say K. Okay, now let us assume that this reaction is a zero order reaction with respect to reactant A. Okay, so basically we will write the rate as K into A raised to power 0 because we are saying that it is a zero order reaction. Okay, now one important question that I want to ask over here is, looking at this reaction, can we say that this reaction is elementary reaction? No, we cannot say that this reaction is elementary reaction because we know that its stoichiometry is 1 but its order is 0. Okay, whenever order and stoichiometry are same, then we can say that it is a elementary reaction. Okay, in some cases it might happen that like the stoichiometry and the order is coming out to be same, but it might not be a elementary reaction. So we'll say something like this: if a reaction is elementary, okay, if a reaction is elementary, the order will be same as that of stoichiometry. Okay, but if order is same as that of stoichiometry, we cannot always say that the reaction will be elementary. Okay, I hope this point is clear to everyone. So basically rate is equals to K into concentration of A raised to power 0. So this will never be a elementary reaction, this has to be a complex reaction. Okay. Now we can also say that rate is also defined as minus dA by concentration change upon dt. Okay, this we have done in the previous lecture, that we write instantaneous rate as minus dC by dt. So basically I am directly writing, instead of C, A, that means concentration of A. So minus dA by dt. So this is the rate. So this will be equal to K into A raised to power 0. So this is basically called as differential rate law. Okay, because we have written a differential equation. So this is called as differential rate law. Okay. So what we are doing is we are taking a reaction, hypothetical reaction in which A is changing into B, and we are saying that let us assume that the rate is that the order of this reaction is 0. So basically the rate equation or the rate expression for this reaction would be rate is equals to K into concentration of A raised to power 0, right, because the stoichiometry and this coefficient are not matching. That means we can surely say that this reaction is not a elementary reaction. Okay, so this is a complex reaction. So basically we will say that rate is independent of concentration of reactant. Okay, so here because this is something raised to power 0 is always 1, so rate is independent of the concentration of reactant. So a very important point over here, in a zero order reaction, rate is always independent of concentration of reactant. Okay, so suppose you have started a reaction with say 2 molar. Okay, you got some rate, you increase the concentration of the reactant say to 4 molar. but the rate came as same. It means that it is a zero order reaction. That is, the rate is independent of the concentration of the reactant. Okay. So basically, if I write rate as change in concentration upon time, like we are writing expressing in terms of instantaneous rate. So this is basically minus d concentration of A upon dt. This will be equal to k into A raised power 0. So this is basically called as a differential rate equation or rate law. Okay. So basically we are going to integrate this and find the integrated rate law for zero order reaction. Okay. So we are going to derive the integrated rate law for a zero order reaction. So we'll take this differential equation, this is minus, this is just a concentration term, this is equal to k into A raised power 0, A raised power 0 is 1. So we'll write this as minus dC or concentration of A equals to k into dt. Okay. So now we have to integrate at time t equals to 0. When we started this reaction, there would have been only A present. So let us assume the concentration of it to be A naught. Okay. Now suppose after say some time t, the concentration of reactant would change, and suppose it is AT. Okay. So square bracket is just representing that it is a concentration term. Okay. So don't get confused over here. So this is the basic integration that we have to solve. We know that integration of dA would be A. Okay. And the upper limit over here is AT and the lower limit is A naught. So just square is just representing the concentration. We could have written A also, but square bracket indicates it is a concentration term. So this will be K, integration of dt is T, upper limit is T, lower limit is 0 with a negative sign. So when we do this, so it becomes AT minus A naught, okay, with a negative sign outside. This is equals to KT minus 0. Okay. So when we rearrange this, this becomes A naught minus AT equals to KT. Okay. So this becomes the integrated rate law for a zero order reaction. Okay. So this expression is now very important. So this is basically integrated rate law for a zero order reaction. I hope this is clear to everyone. This is just a basic integration which we are carrying out. I hope this is clear. Okay. Just write it down quickly. So A naught is the initial concentration, that means when we started the reaction, and AT is the concentration after time t. Okay. K is the rate constant of this reaction and T is the time taken for this transformation. Okay. So this becomes the integrated rate law equation. Okay. So this is a very important expression which we are going to use. Okay. So just write it down. Okay, 2-3 very quick points. Now because rate is proportional to concentration of A raised power 0, so we will say that rate is independent of concentration. Now we have seen that because its order is 0, so it cannot be an elementary reaction, right. So it is always a complex reaction, and we have written the differential rate law, and then we have integrated it to find the integrated rate law. So the integrated rate law is A naught, that is initial concentration, minus the final concentration equals to the rate constant into time taken. Okay. So I hope everyone has written this. So now let us discuss the characteristics of a zero order reaction. Okay. The first point is the rate of a reaction is independent of the concentration of the reactant. Okay. Now we have already written that rate is equals to K into A raised power 0. So basically rate is equal to rate constant, so it is independent of concentration of the reactant. So if we draw a plot between rate of the reaction with concentration, so we know that this will be a constant. Okay, so this will be a constant parallel to concentration axis. Okay. Now the second point is the concentration of the reactant decreases linearly with time. Okay, so we also derived the expression that A naught minus AT, concentration of AT is equals to KT. So we can say that concentration of A at time t is equal to concentration of A at time t equals to 0 minus KT. So basically this is a linear equation. So if we plot the concentration versus time graph, okay, so we know that this equation concentration, so this is y is equals to mx plus c type of equation. Okay, so the intercept in this case would be A naught. Okay, we are plotting with time, the slope will be minus k. So basically let us assume that the concentration is A naught over here. So basically this is a straight line, okay, with a negative slope and intercept of A naught. So basically this is going to have a slope of minus k naught, minus k. So we can say that we can record this angle theta and slope is tan theta. So basically because it is an obtuse angle, so tan theta would be negative, so slope is minus k, so we will get the value of k. Okay. Just draw this graphs also. Graphs are very important for different order of reactions. Okay. So basically the characteristics of a zero order reaction is that the rate of a reaction is independent of concentration and the concentration of the reactant varies linearly with time. Okay. The next important is the unit of rate constant. Now we know that because rate is equals to k into concentration of A raised power 0, A raised power 0 is 1. So basically rate is also equal to rate constant. So the unit of rate constant in this case would be same as that of unit of rate of the reaction. Okay. So the unit of K would be moles per liter per second. Okay. So I hope this is clear. Okay, the next important is half-life time period. So basically half-life time period is written as T half. Now what is exactly half-life time period? Half-life means half of the reaction has taken place. Half-life time period is the time required for a particular reaction to react or to decrease its concentration to half its original concentration. So basically half-life time period is the time when the concentration of the reactant becomes half. So it is the time taken by the reaction to reduce its concentration to half of its original concentration. Okay. So basically suppose we are having any zero order reaction. So we know that the rate equation is A naught minus AT is equals to KT. Okay. So when we say that half-life time period is the time taken by the reaction to reduce its concentration to half of its original concentration, or we say that half of the reactant has reacted. Okay. So initial concentration was A naught. When half of the reactant has reacted, how much reactant will be left? Again half would be left. So basically AT would become A naught by 2. Okay. So basically half-life time period is the time when half of the reactant has reacted. Okay, so basically when half of the reactant has reacted, the time taken for this would be called as half-life time period. So suppose we are having this hypothetical reaction A changing into B, suppose its initial concentration was A naught. Okay, so when half of the reactant has reacted, that means how much? So this is the A naught, which is concentration at time t equals to 0. When half of them has reacted, okay, that means how much would be left at this time? So this is again A naught by 2, and half of would this be formed. Okay, I hope this is clear to everyone. So when half of the reactant has reacted, so obviously half is still left, so basically AT becomes A naught by 2. So when you calculate this, so this is basically A naught by 2 is equals to K into T half. So we replace the T by T half, so basically T half is A naught upon 2K. Okay, so this is again a very important expression. So basically half-life time period is the time when half of the reactant has reacted. Okay, when half of the reactant is reacted, so half is reacted, that means A naught by 2 has reacted, so A naught by 2 will be left over. Okay, so AT would be A naught by 2. Okay, I hope this expression is clear to everyone. So if you plot, okay, just write it if you have not written. So if we plot the half-life time period with concentration, okay, with the concentration, okay. So with the initial concentration, so we'll say that T half is directly proportional to initial concentration, okay. So basically this would be the graph, and slope of this would be 1 by 2K. Okay, so I hope this is clear to everyone. Okay, so the T half is equal to A naught by 2K. So now a very important point is a zero order reaction always goes to completion. So let time of completion be Tc, okay. We are writing this as Tc. Now if we look at the graph, okay, this initial graph, we said that this is the graph, so you can see that this is the time when the concentration of A is reducing to 0. That means this reaction has gone to completion. That means entire of the reactant has reacted. So this time would correspond to Tc. Okay. So in this case, when the reaction is complete, it means that the final concentration of A is 0. Okay. So when the reaction or when the reaction has gone to the completion, it means that the entire A has finished, or the final concentration of like AT is 0, okay, the final concentration of A is 0. So in that case, we know that A naught minus AT, concentration of A at time t equals to 0 minus concentration of A at time t was equal to K into T. Now when the reaction has completed, it means that AT was the final concentration of A, so this would have been 0. So we'll say that this is K into Tc. So basically Tc is equal to K upon A naught. Okay, so again a very important expression which you should know, that Tc is equals to K upon A naught. So T half was, okay, just we have derived this in case you forgot. So this is just T half was A naught upon 2K, okay, and Tc is time of completion is A naught upon K. So we can say that T half is Tc by 2, okay. So a zero order reaction always goes to completion. So the next very important point is and the time required to complete that reaction is rate constant, the value of rate constant upon the concentration, initial concentration of the reactant. Okay. And the last very important point is that a zero order reaction must be a complex reaction. Okay. So, just write it down. So, just I will clear it from here. Okay. So, I can write this expression as, so basically Tc is equals to A naught upon K. Okay. So, this is the time of completion. Okay. And we say that a zero order reaction is always a complex reaction. Okay. So, just write it down. Okay. So, let us take some examples of zero order reaction. Now, very common example is a photochemical reaction. Now, whenever you are seeing any photochemical reactions usually are zero order. So, if you combine H2 and Cl2 in light, we will get HCl. Okay. Or if you are decomposing any substance on solid surface, something like N2O. So, suppose you are decomposing N2O on platinum surface into N2 plus O2. So, this will be again a zero order reaction with respect to N2O. Okay. Decomposition of ammonia in presence of molybdenum or tungsten. So, whenever you are decomposing ammonia on the surface of molybdenum or tungsten, it will be again a zero order reaction. So, any reaction that is photochemical in nature or carried out by light will be zero order reaction, or any reaction which is occurring at the surface of a solid is a zero order reaction. Similarly, decomposition of Hi on gold surface. Okay. So, this is also zero order with respect to Hi. Okay. So, just write it quickly. We will solve one or two questions on this as well now. Okay. So, let us take one question. For a zero order reaction A changing into B, the value of rate constant has been given to us. Find the concentration of A and B after 10 minutes if we start the reaction with say 10 molar of A. Okay. Just solve this question. So, basically because it is a zero order reaction, we know that this is the integrated rate law, okay, where A0 or the A naught is the concentration of A at time t equals to 0, At is the concentration of A after time t, K is the rate constant. Okay. So, we need to find the At, concentration of A at time 10 minutes. Okay. So, this will be A naught minus Kt. So, we know the A naught is 10 molar minus the rate constant is 0.01 molar per second it is given, and we have to calculate after 10 minutes. So, we have to convert this time into seconds. So, basically this will be 10 into 60. Okay. So, basically this will be 10 minus 6. So, basically the At would come out to be 4 molar. Okay. So, the concentration of A after 10 minutes would be 4 molar. Now, because initially we had 10 molar, okay, say after some time t, we are left only with 4 molar, that means 6 molar of A has reacted. So, the amount of B found would be 6. Okay. So, this is a very simple question just based on the expression. Okay. So, initially 2 or 3 lectures will be very easy, basically dealing with the formula so that we become accustomed to the formula, and then we will take the higher level problem solving. Okay. So, let us calculate this. Now, this says that for a zero order reaction A changing into B, find the ratio of T 3/4 and T half. Now what is T half? T half is the called as half-life time period. It is the time when half of the reactant has reacted. Okay. So T 3/4 will be when 3/4 of the reactant, that is 75% of the reactant has reacted. So T 3/4 is when 75% of the reactant has reacted, T half is when 50% of A has been reacted. So basically we have been said to calculate their ratio. Okay. So to calculate the ratio, we have already derived that for a zero order reaction T naught is, T half is A naught upon 2K. Okay. So we need to derive T 3/4. So we'll just use the expression A naught minus AT is equals to KT. Okay. Now when 3/4 of this reaction has occurred, say suppose this was A naught initially, 3/4 of the reaction has occurred, that means 75% has reacted. So how much would be left? So basically A naught by 4 or 25% of reactant A would have been left. Okay. So T 3/4 is basically the time taken when 75% or 3/4 of the reactant has reacted. So 3/4 has reacted. So it was initially A naught, so 3/4 A naught has reacted. So the left would be A naught minus 3 A naught by 4. So basically AT becomes A naught by 4. Okay, so this is equals to KT. So I can write this as 3 A naught upon 4 equals to KT 3/4. So basically T 3/4 will come out to be 3 A naught upon 4K. Okay, so just we have to divide this. So this is basically 3 A naught by 4K divided by A naught upon 2K. So we'll just cancel this out. So this will be cancelled. So we'll be remaining with 3/2. So the ratio would be 3/2. So for a zero order reaction, T 3/4 is 3/2 times T half. Okay. So T 3/4 is 1.5 into T half for a zero order reaction. Okay. So I hope this question is clear to everyone. So you need to understand the significance of these time. Okay. The last question, just look at this question. This says that for a zero order reaction 2A changing into B, find the, okay, so this is just the find the value of T half. Okay. So basically we have to find the value of T half. Now we have derived T half for a zero order reaction as A naught upon 2K. Okay. So this was what we had derived. Now will T half for this reaction will be same or not? Okay. So when we are deriving for this, when we are deriving T half, we were deriving for this reaction A changing into B. Okay. Remember we assume that A is changing into B and rate is equals to K into A raised power 0. So the T half is corresponding to this zero order reaction, but you can see there is a 2A over here. So okay, so we have to again derive for this. So we'll say that rate of that reaction is K into A raised power 0. Okay. Now we know that rate is minus dA, change in concentration of A, upon dt. Because we are writing the overall order, so we have to divide this with the stoichiometry. So basically in this the rate was K into A raised power 0, because stoichiometry was 1, so the overall rate was minus dA by dt. This was equal to K A raised power 0. Okay. So this is again a very silly mistake that most of the student makes. They don't see the equation, just it is written zero order half life, so they just use this formula. So just see that the reaction is this, then only you can use T half as A naught by 2K. So this is a very common mistake that everyone makes. Okay. Because there is a factor of 2 over there, so when you are writing the overall rate, so a factor of half will come there. Okay. So this is equal to K. So basically minus dA by dt will become equal to 2K. Okay. So when you derive this, so we'll get A naught minus AT equals to 2K. 2KT. Okay. So basically K would be replaced by 2KT. So in this case we will say that AT minus A naught, or for half-life time period we will say that, to calculate half-life time period we will say that it is the time when half of the A has reacted. So half of the A remains in the solution. So it will be A naught minus AT would become A naught by 2. So this is equal to 2 KT half. Okay, so this will become 2 A naught by 2 equals to 2K into T half. So T half of this reaction would be A naught by 4K. Okay, so this is a different expression than that. So just take care of the stoichiometry. Now the shortcut of this is the factor which is there in the stoichiometry. Okay, if it is 1, then it is simply A naught by 2K. If it is 2, this will become 2 into 2K, because like when you are writing the expression, this will become 2K. So if any factor is there, say this is a factor of N over here, so N A changing into B, and suppose you have been said that this is a 0 order reaction, so the T half of this would be A naught upon 2 NK. Okay, so you can integrate and find it out, or you can just have the shortcut that whatever is the stoichiometry, I have to write this with K. Okay, so if it is 1, then it is only K. If it is 2, then we have to write 2K. If it is 3, then we have to write 3K. Okay, I hope this is clear to everyone. Okay, so this is it for today. So we have basically covered a 0 order reaction, some examples of 0 order reactions, okay, and some numericals involving 0 order reaction and finding the order of reaction. Currently we have missed a topic known as molecularity, which I am going to discuss in the next class, because molecularity is also very important as like order is. So basically in the next lecture we are going to cover about molecularity. We are going to take some more examples of 0 order reaction, and we are going to start with the first order reaction, and from there the level of the chapter will increase and we will go on to solve higher level problem solving. So a daily problem sheet has been given to you in the app. You can find the daily problem sheet, you can solve it. So basically it is an elementary sheet. So whatever we are covering, we are ensuring that you are solving that portion so that the concepts are revised well. So just go through the lecture, understand the theoretical aspect. Okay, once the level is done, once we have established a good level, we will definitely jump onto the higher level problem solving, and the sheet which you will get will obviously become more difficult. Okay, so this is Animesh signing off for now. If you have any issues, any doubts, you can put that in the chat box. I will definitely get back to you. Thank you, students.